Hello everybody. Today we will speak about the other type of amplitude modulation. Last lecture we speak about the AM modulation. Today we will see how to fix the problem with the AM modulation, the high power, and how to widen the channel bandwidth. We say last lecture that we have double sideband suppressed carrier modulation and single sideband submodulation and vertical sideband modulation. This is as modifications of the amplitude modulation. So first, the double sideband suppressed carrier modulation consists of the product of the message and the carrier wave. So we remove the carrier power here. This is the only advantage. Okay, so we save the transmit from the transmission the power signal or the carrier signal from transmitting it. Okay, so here the S of t equal to C of t, the carrier signal, multiplied by the message signal. In the Fourier transform, you see it as the cosine, you see it as a sigma at f of c and at minus f of c. So it is multiplied by m of t, so it will be m of f minus fc and m of f plus fc. So you see it here as this is the signal, the m of t, and this is the s of t after the modulation. Now in the frequency spectrum, you see this is the signal m of t and m of f here, of course, and here after the modulation you see two at the f of c. However, if you remember, you didn't see here the sigma function for the carrier wave. Okay, so as an example, I want to send a signal which is a sinusoidal signal with amplitude AM and frequency FM with a carrier of amplitude AC and frequency FC. So the frequency spectrum is AM sigma delta F minus FM, this is delta, sorry, plus AM delta F plus FM. So if I make the equation here, this one, so I should shift both of them at FC one time, at minus FC at one time. So the two side frequency for positive frequencies will be FC plus FM here, FC plus FM and FC minus FM, and here minus FC minus plus FM and minus FC minus FM. Okay, so this is minus minus plus plus. Okay, so here as you see here, this is all of them for the positive and negative frequencies. As you remember, the negative frequency as just an image in the with respect to the origin, but in the reverse side. Now for the detection of this signal, coherent detection, the recovery of this signal can be accomplished by first multiplying the S of t with a local generated signal. So locally generated in the receiver, we generate f of c, cosine f of c, and multiplied by the received signal, the modulated signal, S of t, and then we apply the low pass filter to recover the signal, to demodulate the signal. Let's see how that happening. F of here, S of t, we will multiply it by cosine 2 by fct plus phi. We will see what is this, and multiply by, and this is the amplitude of the generated signal. Okay, and generated in the oscillator here. Okay, now generated sinusoidal wave. So if you remove S of t and put as it's here in the signal, C cosine 2 by fct multiplied by the signal mt, you see here as two cosine multiplied by each other. Two cosine multiplied by each other. It is from trigonometric calculus. It's you take the summation one time and you take the subtraction one time. Here if you take the summation to FC by FCT, so then you will have 4 by FCT plus phi, and here if you take the suppression or subtraction, you will get only phi. This is what we will remove by using by using the filter, and this is here what we have, the signal that we want to recover. M of t multiplied by something here. This is just a phase, and this is amplitude. So this is the block diagram of the coherent detection. Now there is a problem in the coherent detection, is the cosine phi. This cosine phi affecting the signal. This is just out of phase by phi, which is a problem or error in phase. Okay, so a zero demodulated signal when occur for phi equal plus or minus pi over 2. This is, we call it phase error in the local oscillator. This is making attenuation by a factor equal to cosine phi for the signal, the detected output. So to remove it, here this is the output of the coherent detector. Here after we make the subtraction, and after we multiply by the cosine the local oscillator sinusoidal wave, you find that we have this one. This is the signal cosine phi multiplied by a value amplitude, and the other type. So we can just make a signal for the this is we call it the demodulated signal, but multiplied with something here. We can fix it later. So this is if you use a filter, then you make a filter around 2W, and then this will be discarded as this both of them at very high frequency. Now to fix this, we will see that Costas receiver is trying to remove this problem cosine phi by detecting what is the error, okay, by having something like a feedback. So Costas receiver is consists of 2 coherent detector, but one oscillator in phase and one in quadrature, quadrature phase. Quadrature phase meaning that's not in phase, the other side, the other phase. So if it is cosine, the other one will be sine or reverse. Phase control in Costas receiver, this is the modulation. So we'll make a phase lock and re-established with the appearance of the modulation. So let's see here. This is the Costas receiver for the demodulation of the double sideband subcarrier with removal of the carrier. So we have, this is a signal AC cosine 2 by FCT multiplied by the M of t. You take it as in the coherent detection multiplied by the, this is the phase, the voltage controlled oscillator. The oscillator make a product of a cosine wave or a sinusoidal wave at a specific frequency, but have some error. Okay, so as you multiply by the detected signal and apply the low pass filter, then you will have the M of t, and there is, this is the phase that we want to remove. The other side here, we make a minus 90 phase shifter. Minus 90 phase shifter, this is will give us a sine, okay, but with the same phase. And if you multiply by the cosine, then you will have a 1 over 2 AC sine theta M of t. So you have the signal, your signal multiplied by 1 time multiplied by cosine theta phi, and 1 time multiplied by sine phi. Here we apply a phase discriminators to remove the phase and or to detect the phase, to know what is phi, and then go back to the oscillator to generate the cosine again without the phase, without we're trying to detect the phase. So we have at the final removal of all this cosine theta, and we get only m of t. Now I want to ask you, this is the first question, how is this phase discriminator applied? How it's remove this cosine or detect the phi? What's happening inside? Okay. Now there is another type of modulation, we call it quadrature amplitude modulation. You will get in details with quadrature amplitude modulation later, but let's have a idea about it. It's just like you enable two double sideband suppressed carrier modulation. So you one time send cosine 2 by fct multiplied by the signal AC, and the other quadrature, the other phase, the sine. So instead of sending one signal, you send two signal, which is occupy the same channel bandwidth, but you make use of the bandwidth that you have. The recovery of the receiver of this signal, you just apply two coherent modulation, one time at cosine and one time at sine. So here you multiply here the message. This is the transmitter and this is the receiver of the quadrature carrier multiplexing. So this is the two signal. One time you multiply by the cosine and minus 90, so you have sine and you multiply by sine. This is to generate this signal, and then you take the summation, then you send it. In the other side, I will apply the coherent detection, but one time with cosine, one time with sine, to the same idea. This is the normal cosine and sine, and you will recover 1/2 AC dash. This is the amplitude of the oscillator, the sinusoidal wave from coming out of the oscillator, and here we have the M2 signal. Okay. Now the other type of the modulation, we say there is three: double sideband, single sideband, and vestigial sideband. So single sideband, we only here send one side of the signal instead of two sideband in the double sideband. Okay, so because the signal already known around the origin, and it's like the same information but reverse. So we want to send as low as possible from the signal to decrease to increase the efficiency by decreasing the transmitted power and the transmitted bandwidth, so we can send other information or other signals. So the double sideband AM cosine 2 by FM, this is the double sideband, and if you multiply by the C of t, then you multiplied by signal, sinusoidal signal at FC, and you have the M of t at FM. Then you have cosine cosine. Then if you use the trigonometric, then one at FC plus FM and one at FC minus FM. Then we only, this is the two sideband, we only want to send one sideband, so we suppressing this one, we will suppress the other one, so we only have one sideband, or we suppress this side. So for a signal, for example here, this is the one sideband FC plus FM, we will recover it again. FC double the signal or summation of the signal, it's cosine cosine sine sine, so cosine FC cosine FM minus FC sine FC sine FM. Or this is for the upper sideband. For the lower, just here you minus, you make it positive here, and cosine cosine sine sine. Okay, so this is the signal that you will send in if you want to send the upper sideband or the lower sideband. What's meaning by the upper or lower? Here in my signal, I have, this is the signal, this is the upper sideband. We make this is the upper sideband, and we name this side, this is the lower. Both of them are symmetric around the origin. So if you send only one part, then you can recover the same information. Instead of sending two part and you waste two W, instead I will just send one W. Okay, so this and without without the carrier. So here after we have this one, we have the sinusoidal single sideband modulated wave, even minus or negative, whatever it is, whatever you want to send. For a periodic message, then you will have not only cosine 2 by fm, you will have an n of train of n, for example, n multiplied by cosine 2 by fn. Then you will just put your signal in the cosine and in sine here. Okay, for another signal, m dash or m hat, then you just put the m hat in your signal. Okay, so I can send the m of t in the cosine, and I can send m hat, which is another periodic signal, in the sine here, this type. This is another idea. So under the appropriate condition, the Fourier series representation of the periodic signal converges to the Fourier transform of the non-periodic signal. So we will take as information, or we take note from that we can represent the signal. Now another thing, the Hebert transformer is just a phase shifter, but a wide band phase shifter. So it's phase shifting a signal with a W frequency. Frequency response characterized in two parts as follow. So the signal we will just multiply by the signum function, if you remember signum function, minus j signum function. Okay, so the magnitude is unity, the same for positive and negative sides, but the phase is the response is plus 90 for the positive frequency. So the positive side will be phase shifted by 90 degree. Okay, now let's see here. This is the signal that I want to send. This is the M of f. This is the two sideband. So in order to use the single sideband, I have to have a signal that there is a difference or a gap between the two sides, so I can recover it. This is the upper sideband, different shape of the signal. It doesn't have to be a triangle. So, and this is the lower sideband, but there is a difference between them. There's a shift. Okay, so when I multiply by the sine and cosine, I will shift it here to the f of c. Okay, and this will be the upper sideband, and will be the lower sideband. Then I will just use a filter around the upper side to suppress the signal. Here we said we will suppress one side of them. So how I can suppress one side? By using a filter around the upper side or around the lower side, then I will get the other type. So the other side will be removed. So this is what's happening here. Now this is the modulator for the single sideband. Even frequency discrimination method using band pass filter, only around a certain separation, but this is there is must a certain separation between the two sideband, so I can use the band side. This is what I said here. And the phase discrimination method, which is you discriminate the signal by changing the phase, so it will be in the null point of the other side. Okay, by using the Hilbert transformer. Okay, so you use Hilbert transformer to phase discrimination of the one of the sides. Okay, so to interfere with the in-phase path to eliminate the power in one of the two side bands, depending on whether you want the upper side band or the lower. So here, this is the frequency discrimination. You just have the signal multiplied by the cosine, and you apply the band pass filter to the desired side, to the upper side or the lower side. This is the phase discrimination. Here I have the signal. I just multiplied by the cosine. There is the oscillator at FC, and there is the wideband phase shifter, and here this is the minus 90 phase shifter. So I have sine 2 by FCT, and there this one wideband phase shifter, it will shift the signal, shift one side of the signal to be 90 degree, and multiplied by the sine 2 by FCT. Then I will have, like, you have both of them at the same place, for example, so it will be removed. Okay, you're removing one of the side by changing the phase. Okay, so here I want you to, this is the second question in this lecture. I want you to describe mathematically and in written words how that's happening, how that the wideband phase shifter or phase discrimination happened. So how I can remove the one side, the upper side, and the lower side band of the signal. Okay. Now the detection, I remove one side, I send it, transmit it in the channel. Then I want to detect the signal. First, I use the coherent detection. The synchronization of the local side should be at the same FC, and with the responsible regeneration of the carrier in the transmitter, so both of them at the same frequency. But before I demodulate the single sideband, it's complicated because I should add the other part. Okay, so by adding the other part, I just make some reflection or mixing. So up conversion and the unshaded part here, I make F2 equal to F1 plus FL, and FL equal to F2 minus F1. So this is the block diagram of the mixer. I have the signal at F1, the carrier signal. I multiply by another frequency FL, and then I apply the band pass filter with the carrier frequency F2. So this is the signal. This is the spectrum of the modulated signal at F1, and I just apply at F1 here. If you see, F1 equal to F2 equal F1 plus FL. So F2 here, this is F1 here. I will just apply that at FL. I will reflect the signal around it, and the same happening in the negative side. So I will have both part, the upper side and the lower side. Imagine here that this is the one side. This is all one side. As you remember, we have a gap, energy gap in the signal. So imagine that this is one side. I want to reflect the other side. So you'll just make some changes in the mixer, so you can have the reflection around FL here, around FL. You have FL plus F1 and FL minus F1. Then you have this side, and the same happening in the other side. Okay, this is, and if you use a filter, you apply a filter here at this side, you then have your signal, the complete signal, the two side band of the signal, the original signal, the original modulated signal, because in the single side band you already remove one side, even the upper side or the lower side. But in the regeneration of the original signal, I want the original signal that I already, the M of t, so I have to recover the other side, and then when I recover the other side, I have two, one at FL plus F1 and one at minus F1 minus FL. I just use a filter, a low pass filter around my signal, then I will recover the M of t. Okay, next lecture we will speak about the vestigial sideband modulation, the last one in the amplitude modulation. Thank you for listening.